Good afternoon and welcome back to CS240. This is Intro to Computer Systems. And I want to get started exactly where we left off and continue talking about heap and stack memory. So I want to first ask you guys, how many of you guys have dove into at least copying and pasting all the code I provided for you as part of MP3? And what do you get? What do you see when you did that? Did you get a seg fault?
Yeah, on my Mac, but not on my PC.
Oh, okay. I'm a little worried about that because Mac keeps adding these security things. So I'm a little worried that because what I do is I actually inject the malloc into your system library. And I'm a little worried that Mac may have kind of caught up to what I'm doing.
Valgrind doesn't work either.
Oh, yes. Okay, there's this great program called Act that will let you run the Docker test cases on your computer. That may be the best way to do it on a Mac. Or you can use a virtual machine or a Windows box or a Linux box. Okay, so if Valgrind doesn't work, there's no way malloc's gonna work because we're using the same hack that Valgrind uses. Yikes. Okay, so Mac people, that's a fun thing we have learned, but there are workarounds. This will be the only MP that we're really hacking the system, so thank you, Matt. Do you have a question or no? Awesome. What do you see in the output?
I saw the
Yeah, so you had like 10 lines of code, right? And you were able to see every single memory block. And today I wanted to really put this idea of all the memory blocks that you're seeing as part of MP3 into reality. So what we know is when the system gives us memory, we have stack addresses and heap addresses. So this is something that you've seen since 225 days. And the stack starts at really high addresses. So if you have a memory address that has lots of Fs or very, very large, that's generally a stack variable, especially compared to heap variables that generally have very, very small addresses. So what we're going to do is we're going to say the stack is something that the operating system is going to manage for us. We're not going to touch the stack memory. We don't have any control over that. The compiler sets up the stack for us. But as systems programmers, we actually can control malloc. And let's look at how we might think about the efficient use of heap memory. Because a program only has a single heap. The heap has a starting point, and the heap grows up to higher and higher memory addresses. So if the heap starts at address 10,000, we start at 10,000. If we need an allocation of 100 bytes, we're now at 10,100. That heap region is between 10,000 and 10,100 in our memory address space. So we have this heap. And what I have for you is a program very, very similar to the program that you saw in MP3. And I want us to go through that program and actually write out and understand what the heap memory is doing in this program and think about different strategies on how we can be the most efficient as we can about allocating memory. The first thing I want to do is I want to just naively go through this code and look at what the allocation requests are being made. And I'm going to actually start the heap because heap starts at low addresses and grows up. I'm going to grow the heap up just like it does on your computer. So the start of the heap is going to be at the bottom, and as I make allocations, I'm going to grow my heap up. And this corresponds to memory addresses as well. Sometimes people will draw this backwards, where they make the heap grow down. If they draw it backwards, you'll notice the addresses are going to go higher as you go down. I think it kind of makes sense to have the addresses grow just like the heap grows. But there's two different ways of drawing it. Both of them is completely correct. So very first thing, the heap is completely empty, and the size of our heap is 0 bytes. We've allocated absolutely nothing on our heap. And the first line of code that we see on our handout is int star a is equal to malloc of 4 kilobytes. 4096. So what this is doing is this is going to go and ask our system to give us 4 kilobytes of heap memory. So for those of you who started on MP3, what's the system call that's actually made by C to actually go and increase the heap from the operating system? Yeah. Yeah, SBRK, or I call it sbreak. And so SBRK or sbreak is going to the operating system, asking the operating system, please increase the size of my heap. So I need more memory from the operating system to make my program run. So I'm going to call sbreak expand my heap by 4,096 bytes. So now my heap has grown 4,096 bytes. And I'm going to go ahead and just label this very bottom box as OX 10,000. So now my heap has grown to OX 11,000. And I'm now going to go ahead and give memory back for my program to store, because I'm acting as the operating system now. We're going to give some of that memory back to our program to store the memory address or the data associated with A. So I'm going to put an A here to denote that I'm reserving this space for A, and you can do that in your very bottom box. And now I'm going to go ahead and just note the fact that I'm going to print out that A is going to be equal to 10,000. So the pointer to A is the pointer to the very beginning of the address space I gave to the variable A. So A has the address 10,000. And I'm immediately going to go ahead and then free A. So I'm just going to go ahead and cross A out here. And for this first column, I'm not going to do anything with the fact that I freed the memory from A. I'm just going to mark it as freed and move on with my life. Second allocation is B is equal to malloc of 4 kilobytes. So if we're allocating 4 more kilobytes, what do we have to do? Do we have room on the heap to put these 4 kilobytes if we're not reusing space? Not yet, right? We haven't asked the operating system for more than 4 kilobytes. We're not reusing any space. So we've got to go out and ask the operating system for more space. So we got to sbreak another 4 kilobytes. So now our heap has increased to 8 kilobytes in size. The end of our heap is now address 12,000 in hex. And now I can go ahead and put B in this second block. So now our program's heap memory, the amount of heap space that our program needs to run at this point is 8 kilobytes. We've sbreaked twice. And we have a hole inside of our memory. But otherwise, we're giving all the requests back. And here, what is the address of B? What are we going to print out? What's the address of the beginning of block B? Yeah, 11,000, hex 11,000. So B is equal to OX 11,000. Okay, next allocation is C, same idea. So we need to sbreak another 4 kilobytes, get that memory from the system. So I'm going to have C, and now the top of our heap is 13,000. C has the address of 12,000 returned from the system. So anything from hex address 12,000 to 12,000 FFF is entirely accessible to C, and we're reserving it only for C to access it. And then we'll do one more. D is also equal to 4,000. So D is going to get the address that points to right here. So this is the address 13,000. So A, B, C, D. We've got these allocations. We're expanding our heap every time we need new memory. We're seeing exactly what's happening as we expand our heap. We see the memory address that we're returning back to the program based on the memory allocation. Then I'm going to free B and free C. So remember, B is a pointer to here. So we're going to free B. So I'm just going to go ahead and say B, let's get out of here. C, pointer to here. C, let's get out of here. Notice that D is still on the heap. We can't get rid of all of the heap memory. We just have this giant hole now at the beginning of our heap. Because we don't need the memory that was right at the beginning of the heap anymore. But we do have D at the end of the heap. And you can't give back memory partway through the heap, because you only have one heap. You have one contiguous block of memory, that's your heap memory. So we have now a giant hole in the beginning of our heap, and D, memory that we've assigned to the variable D, hanging out at the top of our heap. So after we freed this, E allocation of 5,000. So if E is allocated 5,000, we can go ahead and grow the heap by a little bit more than a block. So we have to give it a whole 5,000 bytes. We're not reusing any freed memory. And we're going to say E is equal to address 14,000. And then we go ahead and do F. F is equal to malloc of 10. So here at the very top, we can stick a tiny little block of F and a tiny little block of G. So these are both 10, and F is going to have an address like OX15200. We got to have enough space to store all 5,000 bytes. And then G might have an address of OX15300 or something. Some address past the end of F. So in this allocation, how much memory do we use? What's this amount of memory that we use if we don't reuse memory? How big does our heap have to grow? Yeah. Yeah, as big as the allocation. So we have 4 kilobyte, 4 kilobyte, 4 kilobyte, 4 kilobyte. We've got, what, 4 kilobyte allocations, right? So 16 plus 5,000. So I'd say 16 KB plus 5020. So we got 4096 times 4 plus that 5,000 and that 20. So we're using over 20 kilobytes of memory. Can we do better? Can we be more efficient? Yeah, definitely. Let's go ahead and run this exact same program through, but doing so where we can reuse freed memory. So I'm going to start at the beginning again and go and make my allocation A. So I've got my heap. Make my allocation of A. We've got address 10,000 to address 11,000. A still has the address 10,000. Nothing has changed. So A is equal to 10,000. I then free A. Next line of code, B is equal to malloc of 4,096. Where can I put B now? Yeah, exactly where A was. I don't have to expand my heap. I'm able to reuse that space. This is great. So now I'm going to say B is also equal to memory address 10,000. So at this point, pointer A and pointer B is actually pointing to the exact same memory despite being those different variables. So even though we malloced each variable, they're pointing to the same memory because we've already freed A. So if we were ever access A, this is a reuse after free error. That we've reused memory after we freed that memory. It's still pointing to memory address 10,000. We just put B there. So that's a whole different variable's memory address. This is how programs get hard and get crazy. Because we've got two variables, and this is why it's always good to say A is equal to null after we free it, because it's going to be far better for us to segfault if we try and access A than for A to screw up B's variable. So generally, after you free, always set your variable to null. And this is exactly why. Then we do allocation for C, allocation for D. So B is equal to 10,000, C is equal to 11,000, D is equal to 12,000. No memory that we can free up. All right, and now we are on line 18. We free memory address B, and we free memory address C. So these are now holes in our heap, and we can do whatever we want with those holes in our heap. So if we get to E, E requires a malloc of 5,000 bytes. What can we do with E? Where can we put E? Is there 5,000 bytes of free memory in a row somewhere in our memory already? Yeah. It's where is it? Yeah, it's where B was and a little bit of C, right? There's like two different blocks that we have to combine to actually get to 5,000 bytes. But this boundary doesn't matter. This boundary was arbitrary. This boundary was just where we said, okay, this is where B ended and this is where C started. But it's all contiguous memory. It's just memory. So it's totally okay for us to say, well, actually, this block right here, this whole thing is now E. And the memory address of E is actually equal to 10,000 as well. So if we don't set any of our pointers to null, A, B, and E actually have the exact same memory address. They're all memory address 10,000. And then same idea, we can stick F and G in this little bit of free space that's remaining. So if we reuse free blocks as efficiently as possible, what's the total amount of memory that this second program, reusing free blocks, has to use up? Yeah, Jake? 12 kilobytes, yeah. 12 kilobytes. So we were over 20 KB versus at exactly 12 KB. So we basically just made this trivial program run in half as much memory by being smart about our memory allocations. This is a huge savings. We don't get this kind of savings all the time. But when we do, this is amazing. Because this is a huge amount of savings for such a simple program. And you can imagine programs that allocate a whole lot more memory are going to save even more memory. And this is the real importance as a programmer of making sure that you actually free your memory after you finish using it. Because the operating system is going to be really, really smart and going to try and reuse as much of the memory as possible. So any questions on these allocations and how the system actually allocates your heap requests when you actually ask for heap memory via malloc, how that actually works? Yeah. Yeah, that's a great question. How do you actually organize where the holes are, right? Yeah, so there's a lot of different strategies on how you can do that. So the way that you're going to get to implement all of this in MP3. This is your MP3. In MP3, I think the way that makes the most sense that's extendable is instead of allocating so if I want to request for 100 bytes of heap memory, I'm not just going to allocate 100 bytes of heap memory. I'm actually going to allocate maybe 120 bytes of heap memory. And at the very beginning of the heap memory, I'm going to store basically a linked list node, essentially. And that linked list node is going to contain metadata about my actual request. So in this linked list node, in this metadata, I might have the size of my request is 100, and its free status is, well, it's used, so I'm going to say free is 0. And maybe, so because it's a linked list, I probably need a next pointer. So the next pointer is some pointer to the next element on my linked list. So there's a bunch of different metadata, and you can decide what all metadata you want. You might want a previous pointer in there as well if you want a doubly linked list. So, but you're basically going to, and because the only memory we have is the heap memory, you actually have to kind of steal a little bit of the memory that the program's asking you for to help you have that metadata about what they're asking about. So that's actually how I motivate MP2 or MP3. So there's other approaches. Some operating systems in the past, and especially for small requests, use like a dictionary approach, where it has, here's a bunch of like 4 kilobyte chunks, and I'm just gonna have a Boolean value to say if it's free or not, and you can just scan that for like the first 0 or 1 value. There's a lot of different approaches, and you can try out whatever you want, because you're gonna get to manage the system. But I think this linked list approach, it's mainly what libc, the actual C library that we uses it well. Yeah, Jake? Yeah. Yeah, so you're saying if I'm allocating E, so E after like all the requests, I have that chunk of 8,000? Yeah, so that's a great question. So we have a state of a heap where initially, now with the actual metadata, our metadata at the beginning, after our request, I think we had a metadata that would say, actually, I don't think, let me see if yeah. So we'll talk in depth about strategies, but if we think about the metadata for these, after all of this is freed, this was B's space, right? This was C's space, and then this was E's space. No, this was D's space, sorry. Right, this is where, if we look at where we are right here, before this line of code runs, do you agree that it's B, C, D stacked on top like that? And the metadata inside of B, at this point, was B is free, and its size is 4096. This metadata says C was free, and its size is 4096. And this metadata says the free is 0 because it's not free, and D's size is 4096. Do you agree with this so far? Are you? Yeah. So at this point, this is actually where this becomes challenging. So we freed block B and C, right? Is there actually 5,000 bytes free in our current block, in our current linked list structure? No. What do we actually have to do to get 5,000 bytes? Yeah, we have to combine the 2 blocks together, right? Was that what you were thinking too? Yeah. So we have to combine these blocks together, and this actually has a technical term. This is called memory coalescing. And to coalesce memory, we have to basically say, well, this is actually one big block of memory. We're going to get rid of the metadata and say, actually, this block down here, it's a free block, and its size is 8192, but we actually get our metadata back. So its size is actually 8292, maybe, if our metadata was 100 bytes. So we actually have to coalesce our memory and make it into a bigger block. Then when we actually grab 5,000 bytes off of it, do we want to just say this entire block is now E? So if we said this entire block was E, we're now giving E 8,100 bytes for just a 5,000 byte request, right? Yeah, it's wasting some memory. So then we also have to split this block and say, okay, E's here, but now we have this new block. This free is 0. Its size is 5,000. Now we have this new block that free is 1, and its size is whatever's left over. So 81 minus, so 3,200 or so. So this is actually a strategy called block splitting that you'll see in MP3 as well. that when you make an allocation where there's leftover memory at the end of the allocation, you might as well just split this linked list block into a used block and a free block. So now this memory is used, this memory is used, but we have this free block in the middle that we can now use for allocations F and G. So basically, all you're doing is you're managing a linked list where you're creating nodes and deleting nodes as you need to use memory. So if you have a large chunk, you have a small request that fits that chunk, great. Yeah, Aaron. Does the save space using virtual memory system? What do you mean? Yeah. Would we be fine with holes if we had, so yeah, if we had a bunch of holes randomly in the middle of our page, or randomly in the middle of our heap, and this was a page. So, because remember, as we talked about, this is actually just made up as a series of operating system pages. So these are pages in your operating system. It may or may not be on a page boundary. And you're right, if there's a hole, this page right here will probably just get paged out when somebody needs your CPU or when somebody needs that memory. It'll get stored somewhere on disk, probably never to be loaded in again, right? But that's still wasting memory because that memory has to be stored because the operating system doesn't know that that memory is never going to be accessed again. So it's going to continually grow the heap. If you look at the program statistics, what the operating system reports is how much RAM this program is using. It's going to report the entire size of your heap. So if you leave this free memory, even though you're never going to use it again, and you just let it hang out there, your program looks like it's taking up more memory than it needs to. And you are wasting some amount of resources and space to save this chunk of memory that you're never actually going to use again. So while the operating system does a lot of things to make sure that the performance doesn't degrade, that just never gets paged into your memory and that's going to stay on disk or stay in RAM and never actually move over to your CPU, that still is going to be less efficient than being able to use it, and it's going to make your program look like it takes up more RAM than it really does. Yeah? Could we imagine a system call where we free pages? We could. Unfortunately, the Linux API doesn't implement that. Or at least I'm not aware of it. So there's no way to basically say, in the middle of my heap, just kidding, I don't want it. Can you just like ignore those pages? I'm not aware of any system call that does that. And certainly, if there is a system call, it doesn't exist in C, like it's not common. Yeah. What's the difference between, sorry? What's the difference between handling memory in Linux and Windows? So Linux is open. We can actually inspect exactly what Linux is doing. So that's why you're going to see almost every class here at U of I, we're going to be like working on Linux. So the MPs, like you're running on Linux. Windows, Microsoft occasionally publishes papers on how they manage their memory inside their operating system. Usually it very closely mimics Linux because Linux has a lot of people working on it, a lot of people developing it, but it's closed source and proprietary. And we can inspect it and like analyze what the bytes are and try and guess at what they're doing, but we're not actually sure. So does Windows have a hacky way of doing this? Possibly, but we don't know. So because we can't inspect the source code, we have to rely on them for telling us, and sometimes they tell us, sometimes they don't. Does that make sense? So basically, we're not sure. Yeah? Yeah, so when you call free in your MP, should you check to see if that block can be coalesced? Absolutely. Yeah, that sounds great. That's what I did in my solution. Yeah. Yeah, as soon as you create a hole, like get rid of the hole. Or get rid of it. As soon as you could, sorry, not a hole, but as soon as you have two blocks in a row that can be combined, as soon as you can coalesce, coalesce. Yeah.
So let's say there's like a heap with like two memory blocks like stacked on top of each other, right?
Yeah.
And like we call it reality on the bottom like memory block.
Yeah. Yeah, so what happens if we have a block of memory that size is maybe 1,000, and we'll call this, remind me of your name? Lloyd. We call this L for Lloyd. And Lloyd, on top of this memory, do you have, what's above it? Is it free or used memory? It's used, okay. So if this, if free is equal to 0, so this memory is used, then we can't expand, and if we want to re-allocate that memory, we can't expand it. So the only thing we can do is we have to allocate new memory somewhere else, do a mem copy to copy all the data over, and then you have that bigger chunk. And then this is free, obviously. So now Lloyd's pointer points to this new memory. If it gets smaller, though, you don't have to do that copy, though, right? And if there's free memory right afterwards, you don't have to do the copy either because you can just expand the chunk, right? So there's a bunch of different conditionals that we can write to make our realloc as efficient as possible. It's like, is it bigger? If it is bigger, is the block right ahead of us free or not? If it is free, can we just go ahead and steal some memory from that block? Yeah, these are the things to think about making memory efficient. And I want to actually combine these things into kind of strategies. So one strategy is the no reuse strategy. This strategy is not good. Uses a ton of memory. So we might use, so no reuse, use a ton of memory. We definitely don't want to do that. Instead, a great heap management strategy is this idea of having free lists. This is the idea that we just talked about, that we have metadata to maintain a list of free blocks in memory. So the idea here is if we have holes in memory, we might have a whole, so we might have a chunk of memory that maybe this free block says I've got 1,000 bytes free, and the next free block might have 500 bytes free, and then the next free block might have 800 bytes free, and so on. And then I might have a free head pointer that points to the first element that's free. So I essentially have a linked list that is spanning through my memory that's connecting all of the free blocks. So we could connect all of the blocks, because we actually have not just free blocks, but we also have free and used blocks. But will we ever make an allocation request to a used block? No. So while you could have a linked list that expands all your blocks, if the used pointer, if the free pointer is set to 0, if it's not free, it doesn't belong on the free list. It'd be a waste of time to actually visit that node. So we might have this list of a bunch of free pointers. And there's a few different strategies on once we have this free list, how do we decide which block to use? Because in your MP3, you're going to end up with this free list. And then it's going to be up to you to use any one of a few different strategies. So one strategy we could use is we can use a best fit. So the idea of the best fit is we're going to go through our entire free list, visit the free list to find the best hole to use. Because if you think about a program over time, you might have a hole of 500, a hole of 800, a hole of 200. There's going to be a lot of holes inside of your memory of various different sizes. And what best fit does is it's going to go through all of the holes in the memory and find the hole that is equal to or larger than the request that's being made, and then use that one that's the smallest hole that's equal to or larger than the request that's being made. So I have a request for 201. I don't necessarily want to make my block of 800 into a block of 600 when I have a block of 250 that I can use for the 201 request. But why don't we love best fit? What's the big problem with best fit? It's slow. Why is it so slow? Exactly. Yeah, you have to search through everything. This is O of n, where O is kind of the number of free blocks. Like it's not even O of n, it's like omega of n. It's always O of n. It's O of n in the best case, O of n in the worst case. So it's always O of n. You're always searching through your entire memory space. So what can we do instead? Yeah, why not do first fit? So visit the list until we find a fit. So I'm going to start at the beginning of my free list, and I'm just going to go far enough into the list until I find the first thing that fits. As soon as I find that fit, I'm just going to use it. So that means if I see an 800 block of memory free for a 250 request, I'm going to go ahead and use that 800 block. I end up with 550 left over, right? So if I'm always using the first fit and always potentially grabbing a larger block, what's happening to the average size of my holes in memory? They're what? They're getting a little bigger? I'm going to say the holes on average are actually getting smaller compared to best fit. Because best fit's going to try and minimize the holes. You're going to try and find a best fit. So you're going to keep these large chunks of memory around, right? But first fit, you might find that large chunk of memory, so the average size of your holes end up becoming these small kind of chunks. So if we think about as you're just finding the first fit, what you end up doing is you find a large chunk, you create that chunk, you basically chop that chunk in half. Now maybe that half chunk isn't large enough to serve the next request. Then you go find another big chunk that in half. So the average size ends up becoming these uniform kind of smaller holes. Does that make sense? So while best fit's going to preserve those big holes for the big requests, first fit sometimes ends up chunking up those holes. So, but the performance of best fit, is best fit's going to be much more performant? Yeah. You don't have to search the entire list. You don't have to, it's O of n in the worst case. When the average case, it might be O of 1 or 2 or 3. Might only need a few requests or a few checks. Still O of n in the worst case, but looks good. So one problem to avoid this idea that we're always finding these kind of beginning big chunks and making them smaller is there's a third strategy that's actually commonly used. And this strategy is called next fit. This is basically first fit, but stores the pointer of the previous search. So instead of starting at the head of the list every single time, the idea of next fit is we've gone through the list, we may have visited a bunch of small chunks that might be at the beginning, and we're going to save that pointer where we're currently at in the list after we found our allocation. And we're going to go ahead and do next fit, where we're going to just start where we made that previous allocation. So we actually end up cycling through our entire heap every single time, or cycling through our entire heap over time, rather than always starting at the beginning. So same idea of first fit. the first one that makes the allocation request, we're going to just take it, so it's very performant. But instead of always starting at the beginning of the list, we actually just save an extra pointer of where we should start our search from. And obviously, if we reach the end of the list, we just loop back around to the beginning of the list. Yeah, first here and then. Oh, so for coalescing the memory, is that always going to be O of n? Yeah, so if we want to coalesce the memory, do we have to go through our entire free list and find out what's before or after us, right? So I'm going to argue that the answer is no. Because if we go back to this drawing, we know this is 1,000 bytes, right? And let's say we're about to free this space up. So we're freeing, this is going to be freed. So this is 1,000 bytes, right? So if that's 1,000 bytes wide, where is the metadata for the chunk that comes directly after me relative to my metadata? 1,000 bytes after. Exactly the length of my chunk afterwards, right? So if I just freed this node, there's no reason I actually need to go through my free list to find out if the person right ahead of me is a free block and I can coalesce with it, right? Oh, yeah. So how do we find out? Because remember, this is just memory. So this memory might be freed as well. We might need to coalesce down as well as coalesce up. How do we get to this chunk? So we don't know how big the previous chunk is, right? And we can't just say, oh, it's 1,000 bytes further up or 1,000 bytes backwards. Any ideas? What would you do? Yeah, maybe a previous pointer is really useful. Yeah, if you just add a previous pointer to the linked list, now I can jump backwards. I like it. Yeah, throw it into the metadata. If you can't reference it through another means, add a pointer to it. I like it. Yeah. I would recommend you coalesce when you're free. Yeah, I mean, could you go through your head pointer and get to where you are in the linked list and then figure it out?
No, wait, so the next bit is for like allocating memory, right?
Yeah.
So,
well, it's for coalescing memory.
Oh, it's for coalescing. Oh, no.
Yeah. So basically, when we have these blocks, we do have to go do the coalescing. So we've got this idea that we can best fit, first fit, or next fit to find the best free block when we're allocating memory. When we do free that memory, we would want to coalesce it. Yeah? So the question is, if you're freeing a block of memory, the only thing that has to be coalesced is the block immediately before and after it. As long as you're continually coalescing, that is true. Storing a doubly linked list might make it very easy to coalesce, yeah? Yeah, you just got to maintain that linked list and make sure that linked list is good. Yep. Yeah, no, this is why free lists are great. And this is why I'm kind of leading you down this design, because it makes a lot of the things that we need to do really easy. So I want to add one other thing here before we finish talking about memory. Yeah?
So if you remove the gap right after you call free,
Yeah.
at the end of the free function, why do you need a free list? Like if you free 1,000 bytes and then remove all the memory down 1,000 after that.
So you need a free list because there's going to be holes. So if we think about a whole memory, this is what your entire memory looks like. You've got a free block, then you have a used block that's been used, then you have a free block somewhere else, then you have a used block, then you have another free block. You can only coalesce blocks that are next to each other. So there's always going to be some used blocks in the middle of your memory that your program's still using. And I have you print out the actual heap as part of MP3, so you can actually see this in real memory. You have that print heap function I gave you. So I want you to be able to see these things as you're programming real code. So you have a stack trace that basically gives you this linked list as part of your MP3 code. So this is all going to look very, very familiar as you're looking through these stack traces. And I encourage you, as you're trying to figure out what's going wrong with your list, like draw pictures just like this. Of I've got this free block, this pointer's pointing here, the next pointer's here, the previous pointer's here. Add the pointers as you need these pointers. So one thing I wanted to mention is there are certain strategies you can use on top of all of this to make your program more efficient. And these are strategies that you can think about using in your program. So we talked about coalescing. So we need to coalesce. We've talked about block splitting, the idea that we need to block split. There's one other strategy we haven't talked about. That is, even if you, so let's say you're using first fit or best fit. Let's say you get a really large request in, a request for maybe 2 megabytes, even though most of your holes are in the kilobyte range. What's going to happen to that 2 megabyte request? What's going to happen as your program runs if you have lots of small holes and you have a 2 megabyte request? What's happening? Is that going to be fast or is that going to be slow? Slow, why? Yeah, so if you've got a 2 megabyte request, a very large request, and all your holes are pretty small, even with first fit and best fit, it's going to end up having to run that O of n algorithm, and it's going to be a worst case scenario where it visits every single block. And by visiting every single block, that's really, really, really slow. So there's one final optimization strategy that you may want to employ. And that's the idea of why do you just have one free head? Why don't you have what we call segregated lists? The idea that we're going to have a free head for blocks that are 64 kilobytes or smaller. Then we can have a free head for blocks that are maybe 2 megabytes or smaller. And we might have a free head for very large blocks. So we might have a small number of finite pointers to beginnings of different free linked lists that are interwoven throughout your memory. That basically, if you have a free block that's very small, you add it to a small linked list. If you have a free block of medium size, you put it on the medium size linked list. Free block of large, you put it on the large linked list. And that way, when an allocation comes in, you can first search the list that's most appropriate for that allocation, skipping over small blocks that are going to be known to be too small. Yeah? Yeah, could you have a pointer that maintains the largest free block and then just check that largest free block? Absolutely. Yeah, you could just have a pointer that points to the largest free block. That would help it for just the extreme of large allocations. I think the most common optimization that segregated list does is because we're probably using first fit or next fit, you end up with lots of small holes that really aren't that useful for medium-sized requests. So the extreme example is that large request, but in reality, it's the medium-sized requests that really benefit from segregated lists. Yeah? Would it ever make sense to find a tree? Sure. Yeah, all of your 225 knowledge, you could throw it in there. So the disadvantage of trees is now you're adding more metadata. So you now have a left and a right child. Remember, you have metadata for every single malloc request you make. So there is actually some amount of effort that you want to spend to think about, do you absolutely need that overhead? So obviously having a tree works out well. I'd say the down trees, if you want the tree to actually be a performant tree, you need to do an AVL type tree. And AVL trees require rotations. That's just getting complicated very quickly. So this is already super complicated as it is. I do agree a tree sounds beautiful. But I would venture you away from that quite yet, unless you finish the MP and just want to nerd out with it. Yeah. Yeah. I would store the next one after that, but instead of a head pointer. Yep. Yeah. So I don't think on the homeworks, I think I have a first fit and a next fit example, or first fit and best fit. I don't think I never have a next fit example because that's kind of implementation dependent. Like I might store the pointer of the current allocation. You might store the pointer of the next allocation. Yeah. Yeah, so if you have a large block that you then block split into a used chunk and a new free chunk, that new free chunk needs to go to an appropriate free list. Well, the linked list doesn't have to necessarily, at least the next free block doesn't have to be the one that's next free contiguous in memory. Because how can you add to a linked list in O of one time? Or, well, usually add to the head, because unless you have a tail pointer. Right? Yeah, because normally you just have a head pointer, so you add it right to the head of the list. That's an O of one operation to update your head to that element and then point it to the old head. So, yeah, if you have a tail pointer, you can add it to the end too. I don't think, in my implementation, I didn't need a head pointer for the malloc. So, we'll do two more questions. Yeah.
If your linked list isn't in order, then how would you make sure that you're coalescing?
So the only thing that you need, so you can always get to the next block based on the size of your current block. Your previous pointer needs to be in stack or in heap order, right? Because that's the only your previous pointer actually has to be contiguous. Your next pointer, because your free list may be different than your, so you sort of have these two structures. You've got this idea of your free list is just going to link elements around. You might keep it in stack or in heap order. You might not. It's not necessary. But I do agree that your previous block pointer absolutely has to be in heap order. Yeah. If I think of it as a vertical structure, I actually would say my head is down here. And then my heap's growing up here, so that's what I would think of it as. Yeah. Any last questions on this? Do you guys have a better feel of what you're going to be doing for this MP? Should be a lot of fun. You're going to have a greater understanding of exactly what's happening with this MP. And this MP is really close to my heart because I actually wrote this MP over 10 years ago. And it's been used every single semester since. Because I used to teach 241. And this MP is the only MP that we use in both 240 and 241. And so this MP, and the thing is the code that's written here is the same basic framework as has been used again and again and again. So when you talk to alumni who got a CS degree here, you can share bonding experiences about MP, the malloc MP. Because they've been here too. Yeah, Aaron. The which list? Yeah. Yeah, that's a great question. Is it worth, like, where's the time trade-off? Is it worth keeping the list in memory order to improve cache efficiencies? Or is it best to make the insertion easy without having to figure out where the list is in a cache order or in a heap order? And I don't know. That's a really interesting trade-off. Like, I don't know if it's going to be, if having a wild linked list that's jumping all around memory is going to be worse off than having a really organized linked list, but taking more time to figure out where's the appropriate spot to put it into a linked list. Because certainly if you have like 10 different linked lists, if you have 10 different segregated lists, figure out like, okay, what's my previous thing that's attached to me? I might have to jump back quite a few elements to figure out what's my previous node. So there's cost in both of them. And that's the beauty of doing systems programming, is we get to decide what's the trade-off we want to do? What's the most efficient approach? And I honestly don't know what's most efficient. I'm going to guess it's going to depend on programs. Some programs are going to perform better with one option than the other. So in the last just 15 minutes, I wanted to make sure to spend a few minutes talking about kind of the course and sort of reflecting on the first half of where we have been in the first, I would say we're halfway through the first act of this course. So I think of this course as sort of having two acts. The first act is really hardcore systems programming, where we're really deep in C, we're doing bit level optimizations, we're understanding how things are linked lists and raw memory. Basically everything we're doing in C, because it's actually easier to do all of this in C than it is to do it in another programming language. That when you're doing Indianness, when you're doing these byte level encodings, this is stuff that C does really, really well. You can't hack into the middle of malloc in any other programming language except for C or C++. You're not able to do that in Python. And we're about halfway through this C spot. And we're going to be then moving on after kind of at the end of Act 1, there's a midterm exam that's coming up in about 3 or 4 weeks. And then we're going to make the transition over to Python. And Act 2 is really going to be all about Python and how do you build web apps knowing everything you know now. Because ultimately what I think most of you guys will be doing a lot of is building a lot of web apps and a lot of web services. Like I see that being the primary stuff you're developing. So this is really giving you a foundation that you understand what's going on when things run slow in Python. What's happening behind the scenes. So I want to kind of at least take a little bit of time and figure out what's gone well, what hasn't gone well, and what should we change to make this class the best it can be.